So we are going to cover survey data analysis in Stata 17. Stata 17 was just released in the last couple of weeks, so I have updated the version of this workshop that was posted on our website a while back for Stata 17. However, I know not everybody upgrades their software right when it comes out. And so if you've got an older version of Stata, don't worry, almost everything we're going to do in this workshop will work exactly as it's written in Stata, probably versions 12 through 16, maybe even 11. I'm not sure, I don't have it back to 11 on this machine. But anyhow, the commands that we're running should work in earlier versions of Stata. Also, I'm probably not going to get through the whole set of notes that are on this web page, and I don't really intend to. The way that I write web pages is that I write down everything so that you can come back to the web page and look at the parts you need whenever you need it. And so it's all written out for you. You're not scrambling looking for notes or looking at a PowerPoint saying there's a sentence fragment here, I wonder what it meant. It's all written out for you, and you can go back and refer to it whenever you need that material. And because of that, I don't really feel the need to make it all the way to the end. And besides, the really important stuff is at the beginning of the workshop. The rest of the workshop is just examples showing how to do things. Once you've seen a few examples, you get the hang of it pretty quickly. And so if we don't make it to the end, don't anybody panic. The workshop is intended to be interactive in that at certain points, I will stop and provide you with questions to answer. Basically, you know, how do you get the mean of this variable? How do you do this? How do you do that? So you can practice writing some Stata code. The example data set that we're going to be used comes with Stata. So you just bring it into Stata with the use command, use HTTP, and then it'll just bring the data set right in. So there's nothing to download. There's nothing to do but copy and paste. If you don't have Stata on the machine you're using, or you just don't want to do that, that's perfectly fine. You can just sit and listen, and you'll still get plenty of good stuff out of the workshop. So before I dive into things, does anybody have any questions? Or Andy, Johnny, Siavash, did I forget to say anything that I was supposed to?
Seems good to me.
Okay, so with that, let's dive right on into the material. I'm going to assume that you have Stata up to date. You can check on that by issuing the update all command. Always keep Stata up to date, just good Stata practice. But this isn't a workshop on Stata, it's a workshop on survey data analysis. So let's start off with the first and most basic question that everybody asks. Why do we even need survey data analysis software to begin with? What is so special about these kinds of data? And when I say survey, I do not mean that you wrote a questionnaire and put it out on the internet with something like SurveyMonkey or Qualtrics. That's a questionnaire. That's something completely different, okay? And so in the reminder email, I tried to make that distinction. It's like, no, it's not that, it's something different. So let's talk about what is so different about these data. All right, so for data that are generated by an experiment or a quasi-experiment, anything like that, the data are unweighted. And what you have assumed, whether you think about it or not, is that you have a simple random sample. What does that mean in practical terms? It means that every person, every element, usually a person, but whatever the population is, any element in the population has an equal probability of being selected into the sample, okay? I understand that in reality, that's usually a laughable assumption. When we do research at UCLA, we try to generalize beyond the folks at UCLA, but we don't really acknowledge the people who are not at UCLA didn't have much of a chance of being drawn into the sample. Nonetheless, the math, the formulas that are used to calculate any point estimate, whether it's a mean, a correlation coefficient, a regression coefficient, whatever it is, and the associated standard error, all of that is calculated based on the math for a simple random sample, meaning that everybody in the population had an equal chance of being drawn into the sample. Now, notice when I say everybody in the population, that means you had to have defined the population to begin with. And that's another topic that we're going to go over in a little more detail, because that is also tends to be different when you have what we call this complex survey data. So the real difference here when we're talking about this survey data is that we openly acknowledge that the participants who are included in the survey did not all have an equal probability of coming in. They had different probabilities of being selected into the sample, and we know what those probabilities are. We're able to calculate those probabilities, and that's the critical part. This is where this stuff is different from, say, a questionnaire that was put out with Qualtrics or SurveyMonkey or any of those other ones, is that with that, you don't know what the probability of selection was. In this situation, you do, and that's the critical point. You're able to calculate the probability with which each respondent is brought into the sample. Okay. Now, there are all sorts of different ways that you can collect the sample from the population, but your first order of business is to define the population. And the different public use surveys actually do have different populations from which they're drawing their sample. For example, NHANES, which is the National Health and Nutrition Examination Survey, their population is the United States, the 50 states of the United States, the District of Columbia, non-institutionalized, and I believe up to only a certain age group. So, civilian. So by civilian, it means that it doesn't apply to folks who are in the military. Non-institutionalized means that you are not in a prison or a jail or some sort of a nursing home situation. So those people, even though they're American citizens, they're not part of the population to which the results from analysis using NHANES can be drawn. And so when you first decide, hey, I'm going to look at NHANES or American Community Survey, current population survey, whatever you're going to go look at, you want to know the population to which you can generalize your results. Okay, so because these are really big, expensive, time-consuming things, these kinds of data are usually collected either by government agencies, sometimes NGOs, or really big places like, say, the Kaiser Family Foundation, counties, something where they've got a lot of resources and a lot of money. You don't usually see this out of, say, just one professor's lab or something. So these are the large public use survey data sets. And what they do once they have defined their population is they go get a sampling frame. A sampling frame is literally an enumeration, a list of all of the members of the population. Now, the European countries often have registries of their citizens, so that's what they use for their sampling frame. In the United States, we don't have such a thing, but we do have, where they try to maintain a list of everybody who is eligible to be in, say, the American Community Survey, the NHANES, some of the other big ones, Current Population Survey, that the US government maintains. And so that's where that list comes from. And they're constantly updating it, trying to keep it accurate. That list also contains a little bit of information about those people, and I'll get to that in just a second. Now, people might immediately say, well, if you've got that list, then you can randomly draw off of that list and select your sample that way. Well, they don't do that for a couple of really good reasons. The first good reason is that it is not efficient either statistically or financially. These things are super expensive to do, and so they really do need to keep an eye on the costs associated with collecting their data. And statistically, you don't want to do that because in almost all human populations, there's like a majority and then smaller minority groups. And if you just have a simple random sample, you might not get members of these other minority groups. And you certainly want to include them in the data set, especially in large enough numbers that you can get stable estimates regarding certain characteristics, such as, I don't know, age or something else. Sorry about that. So they have this list, and what they do is they break it up into strata. It's called stratification, and this is something they do. This is not something you as the end user do. This is something that the collectors of the data do. They break the population up into strata. Strata are groups that are defined either by location or by characteristic, such that each element of the population, each person, belongs to exactly one and only one strata. Okay, so for example, you might stratify the United States by the 50 states in the District of Columbia. You could stratify by gender, by age category, by racial or ethnic definitions, or any combination of those. And then you sample within each of those different strata. And how you sample within the strata depends on the characteristics of that strata. So, for example, in the United States, places like Los Angeles and New York have very dense populations. There's lots of people living in a small space. And so the sampling that they do in those areas is really very different than what they do in places where there are not many people in a large area, such as Alaska or Montana. The sampling, the way they sample there is different because they customize it for the area where they're sampling. And so the cool thing about stratifying is that you don't have to use the same kind of sampling plan within each of the different strata. So once we've got our population stratified, sometimes you might go through and do a simple random sample, and the California Health Interview Survey is one example of that. That's exactly what they do. They stratify the state of California, and then they do simple random sampling within each of those strata. In NHANES, they actually sample what we call a cluster or a primary sampling unit. And this is a large group that they sample first. Usually it is a metropolitan statistical area known as an MSA. It could be cities, it could be counties, whatever it is. And then you go down a step and you say, okay, I've sampled this MSA. Now I'm going to sample, I don't know, zip codes. And then I'm going to work my way down to city block. And finally, I get myself down to an individual. So there can be all sorts of different steps from that first primary sampling unit that you sample until you get down to the individual. And the magic here is that at each stage of this sampling, you can calculate the probability that that unit was brought into the sample. So for example, NHANES has 4 stages of sampling. And so the probability of that unit being brought into the sample is calculated at each of those 4 levels. And at the end, they multiply them all together. And that gives you the probability that that particular individual was brought into the sample. So that's what they do. Now, you would, let's finish up the talk about the sampling weights and then we'll go on about the standard errors. So the sampling weights, that's what we call the base weight, and or the actually you can call it the probability weight. In the literature, it's known as the base weight. And when you read about sampling in most textbooks, that's where they leave it. But in reality, that's not what they do. In reality, they take that weight and they say, look, we need to correct this weight because we know we had errors in the sampling frame. Our sampling frame isn't perfect. Our list of people in the population isn't perfect. We need to make some corrections here. We need to correct for the fact that we went to some people and said, please participate in our survey. And the person said, no, thank you. Right. So that is called unit non-response, because the unit, the person, the element said, no, thank you. I prefer not to participate in your survey. So they correct for that. They rake the weights back to known population totals. So for example, the US government has a very good idea of how many males and females there are in the United States. And so they can rake the estimates from any survey they've got out in the field back to known population total. So there's consistency across them. And finally, they do trim the weights. So, excuse me, after all that math has happened, some weights have become very extreme and they will cause estimation problems. And so they tend to get trimmed. So that is what is known as the final sampling weight. After you have started off with this base weight, you've done a whole bunch of math to help correct the weight, you end up with the final sampling weight. And that is what you're going to tell Stata about. And the important thing to realize here is that the weight is a variable in your data set. It's actually a column in the data set, and that column of numbers is used in the calculation of any point estimate that you have. So for example, if you're going to calculate a mean, that sampling weight gets used in the formula for the mean. It's a different formula than what would have been used if you had just a simple random sample. So one of the questions that I frequently get asked in consulting is, well, you know, they said it was a weighted data set, so I assume that they've done whatever they need to do to the data set and I can just analyze it like normal. No, that's not right. The weight is used in every calculation that you do, and that's why weighted data or survey data are different from unweighted or data collected from an experiment or a quasi-experiment. It's because that weight variable gets used in every single calculation, no matter what it is you're calculating. A mean, a median, a correlation coefficient, regression coefficient, you name it, it gets used. The other thing to notice about the weight variable, like I said, it's just a column of numbers, and they're not round numbers, you know, they're not whole numbers, they all have decimal points and stuff like that. If you sum down that column, you should get a very good estimate of the number of elements in the population. So if you sum down the column of weights in the NHANES data set, you should get a very good estimate of how many people are in the population for that time in the United States. And so that's the sampling weight. Now, if you think about it, if I changed the formula for calculating my sampling weight, well, it makes sense that I'm also probably going to change the formula that I use for calculating the standard error. Excuse me, if I changed the formula for calculating the point estimate, then I probably also changed the calculation for the standard error, and that is also true. So let's see here, we went through sampling weights here. The stratification in the PSU, those will be incorporated in the calculation of the standard error, okay? If your survey, for example, the California Health Interview Survey only use Strata, then that's all you use. Some surveys only have clustering or PSUs, and so that's the only thing that's used. But at any rate, these are used in the calculation of the standard error. And typically what happens is that they inflate or make larger the standard error. Now, I've heard many people say, well, wait a minute, I only care about the point estimate. I don't care about the standard error. Yes, you do. And the reason you do is because the standard error will tell you approximately how precisely that point estimate was estimated, and also point estimate divided by standard error is test statistic. So if the standard error is wrong, the test statistic is wrong. Well, and then of course your p-value is wrong and all the rest of it. But if you ignore the stratification and or the clustering, what typically happens is that the standard error is underestimated. In other words, the denominator is too small, ergo the test statistic is too large. And then of course, you worry about false alarms and all the rest of it. So you definitely want to account for these elements, and that means that you're not using the regular simple random sample formulas, you're using these other formulas. A quick note about stratification. When you read about it in textbooks, the classic textbook example says, we're going to estimate the mean of, I don't know, age. And we have this variable that is closely related to age, and it's got 3 categories. So we're going to stratify this by this variable. And then you'll see the standard error around the estimate for age. You'll see it shrink because of the stratification. Well, that's the way it works in theory, but that's really not how it works in practice for a couple of reasons. First of all, when these data sets are published, there's no way to know, for example, what's going to be the outcome variable. So you would have no idea what to stratify by. Second of all, the stratification is necessary for the collection of the data. It's not something that the end user can determine. And so in reality, the stratification variable can either inflate or deflate the standard error depending on the situation. There's really no way to predict which way it's going to go. So when you have the data set, your first order of business after you find out what your population is that you want to find the variable names for the sampling weight, the strata, and the PSU. And then once you have that, you get the joy of writing the survey set command. And so the survey set command, I'm going to argue, is probably the single most important command that you're going to put in your Stata do file. And this command here is what tells Stata what sets of formulas to be using with your data set. All right, so I skipped over a few things. Let me go back and grab those, and then we'll get back to writing that survey set command. Finite population correction, I don't see it all that much. I have it all written out here. There's the formula. Here's the FPC. Like I said, I don't see it all that often, so let's not spend too much time there. Replicate weights. I do see a lot of replicate weights. I expect to see a lot more of those in the future. What are they? They are a series of variables, and they are call them more or less deviations off of the sampling weight, and they are used to correct the standard errors. So oftentimes you either get the PSU strata variables or you get a set of replicate weights. And the reason replicate weights exist is because I'm sorry to say there are bad actors in the world. And bad actors are people, in this case, who look at a public use data set and then try to go back and figure out who the respondents are. All right. Now, the #1 goal of any agency that releases data to the public is to protect the identity of the respondents. And so these replicate weights, and there's usually anywhere between 40 and 60 of them in a data set. They are, like I said, they're deviations off of that sampling weight. And so you can't go back and figure out who participated because you don't have the strata and the cluster information. Now, they typically release masked strata and masked PSUs to, again, try to obscure who might have participated in a survey. And then there are other statistical disclosure control measures that are taken, and we'll go over some of those as we encounter them. But the main point here is that one of the big goals is to protect the identity of the respondents. And so these replicate weights correct up the standard errors without giving you any way of potentially trying to figure out who a participant was in the survey. It is important to note that there's all sorts of different kinds of replicate weights, and they are not interchangeable. All right, so there's, say, balanced repeated replication, or BRR. There's jackknife, there's successive difference, there's bootstrap, there's, I don't know, a couple others. And so when you're using your software, you look at your documentation and it says, okay, I have successive difference replicate weights. I have to use software that will allow me to use successive difference replicate weights. That's what's given in the American Community Survey and the Current Population Survey. You can't specify those as jackknife when they're successive difference, because you're just going to get the wrong standard errors. I do have a page on that here, and one of the best descriptions of these things was in the Westfall Manual. Now, Westat makes Westvar. It's a point and click interface thing. Their documentation, though, is super awesome, but now you have to email them and ask them for the documentation. It's free, but it's kind of a pain, but it's honestly some of the best doc I've ever seen with respect to replicate weights. So the example data set we're using today won't use them, but you're going to see a lot of them out there. We covered this. If you don't use the weights, you'll get the wrong point estimate. If you don't use the PSU, Strata, or replicate weights, you'll get the wrong standard errors. Sampling with and without replacement. Okay, the only program I think that worries about that is Sudan. We're not here to talk about Sudan, so we're not going to go over that. But the upshot is that most of the time, the math assumes sampling without replacement, because if you sample with replacement, then the probabilities of inclusion change every time somebody comes in to the sample. But the change is so minute that it doesn't really make any difference. And so even though in reality, nothing is sampled without replacement, they always, nothing's done with replacement so that you don't get selected a second time. It does, the math here is without replacement. And usually you never have to specify the different levels of sampling, only the primary sampling unit, not the secondary or tertiary sampling units, because their corrections to the standard errors are so minor, particularly with respect to the computational intensity, that it's not worth it. So we usually only worry about the first level of sampling, and we assume that we sampled with replacement, even though we really did it without. All righty, so read the documentation, of course, but you don't have to read it like start to finish, right? Because that would be crazy talk. You want to read about the population that's being covered. You want to read about the sampling design and analysis guidelines, variance estimation, something like that, so that you know how to do the analysis correctly. And then, of course, you want to read about the variables that you're interested in. All right, so what we're going to do is use this data set here. And this is part of the documentation for Stata 17, but I believe it was also in Stata 16. So it's a ready to go data set. And I did this so that everybody had access to the same data set. We didn't have to spend a whole bunch of time cleaning and doing other things. But that's kind of a double-edged sword, because honestly, the data cleaning and knowing what to do is at least half the battle here. So what I have up here is some example of how you actually go do this, because you're not going to be doing your publications and writing off of this Stata data set. You're going to use the real data off of NHANES. And so what you're going to do is download the Stata or the data set, and they all come down as XPT. That's a SAS extension. They come down as SAS data files. In Stata, you can use the FDA use command to read those into Stata. I sorted on SEQN, which is the unique identifier, and then I save it. And this data set here is now as a Stata data set, but you download this way. It's called FDA use because when you submit to the FDA, you actually do have to submit it as an XPT, or at least you used to have to do that. And so that's why Stata called the command FDA use. Got the NHANES data set right, or the NHANES website right here. If you go here to survey data and documentation, you can see the different years of this is the continuous NHANES cycle, obviously in 2-year cycles, and then the older ones are down here. If you look here under survey, let's see here, survey methods here, and then the sample design right here, you can look here at this document, and in the abstract, it tells you about the sampling design, that it's a 4-stage design, non-institutionalized civilian US population, but only the 50 states and the District of Columbia, none of the outlying territories, and some other information. So all of this stuff here is off of the NHANES website, and then you know, any of the stuff that you're going to download, you can also, you know, just go to here, and then the data sets are here. What happens really though, is that like if you're under the examination data, you'll see that there's all sorts of different data sets, and these are the XPT files. This is what you're actually downloading. And like I said, they're XPT, you download them here, and then you have to do some data management to put them together. And I have my old do file here showing you how to do that. So I just CD is change directory to put myself in. This was when I was doing the Stata 15 one, and then I downloaded it, I sorted and saved. I downloaded this, I saved it here, I brought it in, saved it, all this stuff. And then I used one of them, and then I did the merge, and they are 1-to-1 merges, and I merged all of these together. And then what I did was come down here and put in value labels, because that didn't come down. And in a lot of places I had to change missing. So like the missing code here is 7, and I changed it to dot. For variables that have 1 digit, the missing data codes are something like 7, 8, and 9. When the variable had 2 digits, it's 7, 7 or 9, 9 or something like that. And so you actually have to go through variable by variable to figure out how you need to recode the missing. And this is all, it's all coded like this because this is the way archivists archive data, not the way the analyst would do it. And so there's a fair amount of data management stuff that has to happen before you can actually go ahead and do the analysis. And I bring all that up only because that whole process is hidden when I just do this and I bring in this data set that Stata has already very nicely cleaned up and has ready for us to use. But at least this way we can all be on the same data set. So if you want to follow along and issue the commands, now would be a most excellent time. I would highlight and copy these and paste them into your Stata do file so that you are ready to follow along if that's what you would like to do. So this here is our sampling unit. They renamed it in for this example data set. This is, forget the variable name. Let's see here. Whoops, it's not that one. Back. It's here. Oh, whoops, wrong one. Here. So the variable names are actually in this, the SD, MV, PSU, and this is the same across all the enhanced data sets. This is the weight for the 2-year cycle. So this is the interview weight. INT is for interview weight. There's also a MEC weight. And then the SD, MV, STRA is the stratification. These are the masked PSU and masked strata. So this is actually the command you use with the real enhanced survey data set. So, but they changed the variable names in here so that they were a little bit easier. So this is your cluster variable or PSU. Notice this is a square bracket P weight equals, this is your weight variable, whether it's going to be the interview weight or the MEC weight. This is the stratification. Notice the comma here, and notice these are round brackets. And then we have the single unit centered. Single unit centered is an option that Stata brought in version 10, and you want to kiss Stata for doing this. Okay, this is one of the best things. So this is the issue. Remember, we have strata and we have clusters within strata. Typically, you have 2 or 3 strata within a cluster, maybe more, but usually 2. And the variance is calculated based on there being 2 clusters within a strata. A problem happens though when, for some reason, either due to missing data, due to a subpopulation, specification, whatever, you end up with only 1 cluster per strata. When that happens, you can't calculate the standard error. And well, if you can't calculate the standard error, you can't calculate the test statistic. If you can't calculate the test statistic, you can't calculate the p-value. And if you can't calculate the standard error, you can't get the confidence intervals. And so all you're left with is the point estimate, and then all the rest of your output is missing. And this, of course, is not what people want to see. And so Stata gives you different ways to handle this. Now, you don't see this much in SAS or M+ or R, because what those the authors of those programs did was they chose one of these and implemented it and didn't give you a choice about it. Stata is the only one that gives you a choice as to how to handle that, and they gave you some. So the option is, the default is missing, which means if you've only got 1 cluster in a strata, then you just don't get the standard error. One is certainty, and a certainty is a PSU that was brought in with a probability of 1. That's actually kind of common, especially when the PSUs are cities. So for example, when they sample cities, Los Angeles and New York are always given a weight of 1. They're coming in with a probability of 1 because they have to be included in the sample. The scaled is a kind of just a version of that certainty option, and then centered here centers 1 strata against the grand mean instead of the stratum mean. And so I tend to use this one as my default, but honestly, I've played around with it a fair amount, and rarely do I see really big differences in the standard errors depending on what you select there. So this here is the most important command in the do file. This tells Stata what math to use when you go to do everything else. This says use a weighted estimator, not an estimator for a simple random sample. This is my sampling weight. Correct the standard errors for strata and clustering. I would use different math if this was omitted. I would use a different formula for the standard errors if this was omitted. So this is changing the math that's happening behind the scenes. All right, I want to stop for a moment and ask for questions. We've covered a lot. We're about to get moving really quick through the rest of this. So like I said, the intro part was the important part that you understand. I want to pause for questions. If you have a question, would you please unmute yourself and ask me?
If you use the certainty option, do you have to specify which variables are?
No, no, there is no variable. You just put certainty here. And what it means is that when Stata encounters a single PSU and a Strata, to treat it as if it was a certainty PSU, as if that PSU came in with a probability of 1. So the only thing you would do is change this word to certainty.
What would it do to the PSUs that were not singleton?
I'm sorry, what?
What would it do to the non-singleton PSUs?
All it's doing is affecting how the math regarding that one Strata is being handled. And usually the certainty PSUs do not contribute to the calculation of the standard error. So everything else is going to get calculated as normal. And the certainty PSU tends to get ignored because he's not contributing to the variance.
Okay, thank you.
What other questions today, please?
Okay.
Yes.
Sorry, I'm like definitely a beginner to this. So when you were mentioning cleaning the data, is that something I would have to like learn a different workshop about or different training, or would that be something that Stata or a different software could run for a user when they download like the XPT file and then have to?
The cleaning is something you're going to have to do yourself, and it can be done in any software. Stata is particularly good at it. And I tend to do all of my cleaning in Stata when I work with these data files, but it really depends on the variables that you need to use. So you always, for example, go to check to see how the missing data values were coded. Typically, you will see something like 777 or 7777 9999, something like that, and then you set it back to dot. Other times you will see, I don't know, that they didn't include the value labels. And so you put the value labels on just to make it easier for you to look at the output and know what's going on. But it really is very specific to the data set and to the variables there. The one thing to keep in mind, though, is this is completely independent of the weighting and the PSU stratification thing. So you would clean these data just the way you would any other data set. The whole survey set thing only applies to analysis stuff. It doesn't apply to any of the data management stuff.
Thank you.
Anybody else have any questions? These are good questions. So anybody else?
Yes, one more question. And my question is about stratification and cluster. Could I actually just assume like a gender would be a cluster, male, female, and the stratification could be actually, ethnicity, race?
Gender would not be a cluster. You might stratify on gender, but it would never be a cluster, because a cluster is the first thing that you sample. So you don't sample gender. You might sample a metropolitan statistical unit. You might sample a city block or a county in the state of California. You might sample cities.
Got it. So here in this example, there's no cluster. Just assume that the cluster are built in. Is that right? Because I don't see the comment, anything related to the cluster.
The cluster is right here. I've got it highlighted. It's PSU ID.
Oh, got it.
And this is the variable that accounts for the first level of clustering. And when you look at the data set, scroll it down, well, they don't give the clusters, it's either coded 1, 2, 3, 4, 5, 6, 7, 8, 9, or sometimes it's coded 1, 2, 1, 2, 1, 2 within each stratum. But that's all you see. You don't see anything about, you know, this cluster is really, you know, this part of Los Angeles, and this cluster is really this part of New York, or you don't see anything like that. All you see are numbers usually starting from 1 to whatever, and they've just numbered the clusters. They're not trying to give you any information. They don't want you to have the information about where the cluster is.
Thank you.
Okay. All righty. Any other questions? Okay, so we've issued the survey set command. The first thing we want to do is check and make sure that Stata and the analysts are communicating clearly. To double check that, we use SVY describe. So this is describing the stage 1 sampling units. It echoes that this is our sampling weight. VCE is the variance correction estimator, linearized because we're doing a Taylor series linearization, and we're doing a Taylor series because we have PSUs and strata. If we had replicate weights, we would have something else listed here, whether it was jackknife or BRR. This is the option we gave for single unit. This you could have, if you had a different setup, you could have different strata, but here we just have the strata. This is this, and this is the variable we specified here, and we did not specify an FPC. So we have strata, and like I said, they are just generically numbered 1, 2, 3, 4. You don't know anything about these strata. You're not supposed to, and they're just numbered here. These are not quite consecutive. You don't see a 19 here. That doesn't matter. It doesn't matter what the numbers are. Sometimes they're consecutive, sometimes they're not. It doesn't make any difference. The upshot here is that you have 31 strata. Here we have exactly 2 PSUs per strata. Okay, well, if I have 2 PSUs per strata and I've got 31 strata, I had better have 62 PSUs. This talks about the number of observations per strata, right? So I have 380 observations in this strata. Well, that means one of them has the minimum of 165 observations, and the other one has the maximum of 215, and the average of 165 and 215 is, of course, 190. This is far less interesting than when you have like 3 PSUs per, because then the numbers don't work out quite that easily. But what you notice as you go down here is that you've got at least a couple hundred in all of them, except for strata 2. That seems to be the smallest one. The minimum here seems to be about 67. And if we look down here, sure enough, we have a total number of raw observations of 10,337. The minimum number per strata is 67, with a maximum of 287 and an average of 166. This is basically the meet and greet. Okay, this is how you get to know your data. You say, oh, hi, data, nice to meet you. My name is Christine. So that's what you have there. Peeking ahead a little bit, what's going to be important is the number of PSUs minus the number of strata, and that is going to determine your design degrees of freedom. This is super important because a lot of people think that the degrees of freedom is based on N, which is 10,337, which would be lots of degrees of freedom. It is not. It is number of PSUs minus strata, which in this case gives us 31. We have 31 degrees of freedom. Now, for many instances, 31 degrees of freedom is just fine. If we get down to the part about multinomial logistic, you will see that you can very easily run out of those degrees of freedom. And that will create an interesting situation then. But for now, what you need to know is that your design degrees of freedom is PSUs minus Strata. All right. After all of that, we are finally ready to actually run some commands. Yay! We get to analyze some data. These 4 characters, SVY colon, they tell Stata what math to use for the command. So that's why you want to use this SVY prefix. This contains all of the information that we put in right here. Right, so we issued this command, and that gives us the luxury of using this prefix. So this prefix tells Stata what math to use when we calculate the mean of this continuous variable. All right, so that's what we did. And let's see here. It echoes what we should know, that we have 31 Strata, we have 62 PSUs. Our number of observations, the unweighted number of observations is 10,337. But this is the population size. It's the estimated population size. And this is the effect of that sampling weight. So our 10,337 respondents are weighted back to the population to 117,023,659 people. So this 10,000 represents this 117 million, right? Seems like quite a responsibility, doesn't it? I don't know. I think it does. All right. Anyhow, the mean age here is estimated to be 42 with a standard error of 0.3 and this confidence interval. These are descriptive statistics. It's only been fairly recently that you could get standard deviations and variances for these things. Again, notice it's linearized because we're doing a Taylor series linearization. That's why it says linearized standard error here. If you use the post estimation command estat sd, you can get the standard deviation of 15.5. If you use the var option, you can get the variance. Of course, it's just like in non-weighted data, 15.5 squared is your 240.2795. All right, so we've done our first set of commands. If you want to do this in Stata, you can simply copy and paste the commands into a do file. I always use aorder just to put things in alphabetical order so I can find them. You don't need to do that. They're in a different order. I always do that just so I can actually find variables, but that's just me. There's our survey describe command, and here is our survey mean, so you can of course run that and you get exactly what you see on the web page. There's nothing magical there. Here are our post estimation commands that I ran. If you're not familiar with this notation, this is one of many ways to put a comment in on a command, and I just put in that this is hemocrit. So these talk about values in your blood for albumin, and this is your diastolic blood pressure, your systolic blood pressure. Everybody has copper in their blood. This is a binary variable if you were diagnosed with diabetes. This is a binary variable if you're female or not. Here's your sampling weight. You can go look at that. It is just like I said, it's just a column of numbers there, and some other variables in here that they, some of which are derived and some of which are part of the NHANES data. So you can just copy and paste these commands off the web page and you will get exactly the output that you see here. Notice here when we did copper, and the reason I put this in here, notice this is not our 10,337. This is less. We've got missing values on this variable, and that's reflected here in this population size. We're not at 117, we're down to 103. Okay, so watch for missing values because you will see that it affects the estimate of the population size. When we run this one, we're back up to the total population size. And the reason I have these here is because sometimes people come along and they say, you know what, I can say survey colon mean and put in all three variables. Well, notice, for example, here that when I ran this variable by itself and it didn't have any missing data, that it's 41.98. When I run it here, it's 41.97. It's a little bit different. The standard error is a little bit larger. And that's because we had the missing on copper. We don't have missing on age and we don't have missing on hematocrit, but we do have some missing on copper. And so when you run the command like this, it's doing a listwise deletion. Mean is actually an estimation command in Stata, so it's doing a listwise deletion on you. That's why this is down to the 9,118 and this is down to the 103. And so these values for age and for hematocrit are a little bit different because it's run on a slightly smaller sample. So that's just something to keep in mind when you're describing your data, because the first thing that you do when you're, I don't know, doing a master's thesis, a dissertation, or writing anything up for publication is you do your descriptive statistics. And so you just want to be cognizant of the fact that this will do a listwise deletion on you if you run the command like this. Not saying that it's wrong, but it may not be what you were expecting. So just be aware of that. You can use binary variables here. And when you do that, you get something that looks like this. So if I encoded 1 for female and 0 for male, can anybody tell me what this 0.52 actually means? Can somebody unmute, please, and tell me what does 0.52 really mean?
52% of your population is female.
Yes, yes. So it is the proportion of ones in the data set. In this case, it means that approximately 52% of the population here is female. That's correct. And so honestly, this is how I do it. There's a proportion command. We'll look at that in a little bit, but that's just how I do it. And then after that, because we ran it as the mean, you can use the post estimation command estat standard deviation to get the standard deviation here as well. And sometimes that's needed for reporting purposes. They created a variable called rural, which is 1 for rural and 0 otherwise. And so this means here that approximately, I don't know, 32% of the US population lives in a rural area. I didn't know we had that much rural left in the US, but I guess we do. So there we go, standard deviation. So as it says here, taking the mean gives the proportion of the ones, blah, blah, blah. We've already done that. But you can, of course, use survey tab. And the default for survey tab is to give the proportion. So this number should look really familiar because you just saw it right there. Rounded to a different number, but it's the same thing. Okay, so you got that. But oftentimes when I do this, the proportion's great, but I want the actual weighted counts. And so I can use some options to get me the weighted count. And believe it or not, it's called count, okay? Because that's like kind of obvious. So they call it count, right? So what's the rest of this mumbo jumbo out here? The problem is that in Stata output, they only have a limited number of places to put numbers in. So when the numbers get really big, they exponentiate them. Well, this actually kind of annoys me because I can't report an exponentiated number. You know, I can't put that in, you know, the manuscript that I'm writing. So what I do is I expand the cell width, I give it 15 spaces, and then I format the number. It doesn't matter really what format you use. The G is for general. So, you know, I gave it just a general format so that it will expand out these numbers and I can actually type those numbers or include those numbers in my manuscript, I don't get some sort of exponent thing. And of course, Stata tells you down here that that's what you've got here. I always use the missing option, just in case there are missing data. There aren't any on this variable, but just out of habit, that's what I always do, because almost every other variable in the data set has missing values. So that's just kind of my default behavior there. I can get a crosstab between these two variables by simply putting both variables here before my comma. And so this tells me how many folks are both male and in an urban area, how many folks are female and in an urban area, and the same here for rural. By default, you get the chi-square test here. You don't have to ask for it, it just comes. Typically, you want to use this bottom one, which is the design-based here. I am always very cautious here. And the reason I am always very cautious here is that chi-square is typically very sensitive to sample size. And as you can see, our sample size is 10,000, a little more than 10,000. So you've got lots of power. And typically in survey data sets, I actually have to work to find examples where it's not statistically significant. Now, Andy did a whole workshop on statistical significance and the use and misuse of p-values. I want to emphasize here that all of those things that he talked about are even more important in survey data than in non-weighted data, because you're typically very overpowered. And so using a p-value to tell you what's important can be extremely misleading. I don't know that these differences here are all of that important to me. And so I would never let this tell me what's important. Instead, I'd want to actually look at the real numbers and think about what's meaningful in my research situation, and not just say, oh, great, it's statistically significant, and move on from there, because you're really, really overpowered when you're using the survey data. And so the p-values become increasingly less informative, less important. Okay, so there's tons of options that you can use with Survey tab, and you're better off kind of going through the documentation to find out what's available. There are not as many options available with Survey tab as there is for just the regular tab, but there's still all the useful options are there. So here I used call to get the column proportions here. And so, you know, another way to get proportions is to actually use the proportion command. Believe it or not, you can use that. And so we did the same thing here, and you get this. So let's see here. You can also get design effects, misspecification effects, and a bunch of other things with the ESTAT post estimation command, especially after survey mean. Let's see here, the design effect, that DEFF, it's the ratio of two variances. And what it's trying to tell you is how efficient your sampling is. So the clustering tends to make the sample inefficient. What do I mean by that? I mean that to get the same amount of precision as you would have with a simple random sample, with a clustered sample, you usually need to have a higher N. And so we're talking about precision between what we have with our current clustered sample and a simple random sample. So in the numerator here, we have the variance estimate from our current sample, which is, you know, survey set and the way we have it. And in the denominator, we have the variance estimate from a hypothetical sample drawn as a simple random sample with exactly the same N. So our 10,377. All right, if the design effect is less than 1, your sample is more efficient than a simple random sample, but usually it's greater than 1 and often a lot greater than 1. The DEFT is the same thing, except for it uses standard errors. I don't see the misspecification effects all that much. I do occasionally see some reviewers ask for a coefficient of variation. It's actually the ratio, so it's the standard error of the mean divided by the mean multiplied by 100. I've got the reference here for the Stata 17 manual, and it's supposed to be an indication of the variability relative to the mean in the population, and people like it because it's not affected by the unit of measurement, and so you can look at the CV across different variables. So let's see this really work. We have our survey mean for age here, and EStat effects with no options on it. You get your DEFF and the DEFT. Notice this is about 4, and we're not really surprised. We know that clusters tend to make samples inefficient, and it's something you report. It's not usually something you worry about. It just is what it is. Some reviewers request it. Sometimes dissertation committees will ask you about it, but it's one of those things that it simply is what it is. And if you want your misspecification effects, you can ask for those. EStat size after mean usually isn't all that helpful, but after a bunch of other commands, it is super helpful. And what it gives is the raw n and the weighted n. And then here's our EStat coefficient of variation. And I used the display command here. I grabbed my standard error and I put it here. I grabbed my mean, I put it here. I multiplied by 100, and voila, you can see that I got that. Okay, so I have been, oh boy, I've been going on for an hour and a half. Woo. All right, we are going to pause for questions and then exercises. So let's start with questions. Does anybody have any questions that I can answer? I hear crickets. No, wait, that's my air conditioner. Nope. Okay, no questions. Then exercises it is. Let's see here. I can make that larger. Okay. There we go. So let's try those first 3. If you want to, calculate the mean of albumin. So in our data set, as you recall, we have a variable called albumin. You're going to get the mean of that. You're going to get the standard deviation of that. And then you're going to calculate the weighted and unweighted number of people in each age group. And if you look at the data set, this third variable here is age group. So that variable is already made for you and it's in the data set. Why don't we take just 2 or 3 minutes to go ahead and do that if you want. If you'd rather get up and stretch or go do whatever you need to do, that is a-okay as well. We'll be back in about 3 minutes.
Christine, some people are asking if you can paste the exercises into the chat.
Okay. Let's see if that can happen. Let's see here. Everyone. Paste. There we go.
Thank you.
Okay. Is there anything in the chat that I should be looking at or anything I should respond to?
One person asked again how to get the data. Could you show them again how to get the data into Stata?
Yes. But you got to give a girl a minute because I clicked on the wrong thing. Need to share the screen. I need to go here. All righty. So to get the data into Stata, one up here. And I'll put this in the chat. You put those two, it requires that I find the chat again. Stop share, chat. Just put those two commands into your Stata do file and run them. Okay, so you don't need to download or do anything. You just grab those two, and they're on the web page. You can just copy and paste them off the web page too. All right, according to my clock, 3 minutes has gone by. Does anybody want any more time, or does anybody have any questions? Go ahead and unmute yourself and ask any questions that you may have.
Christine, one person asked about the CV, the coefficient of variation, like what
Yes.
that means.
The coefficient of variation, it is the ratio of the standard error of the mean to the mean. So literally you get the mean and its standard error. You take that standard error and put it in the numerator. You take the mean, you put it in the denominator, you multiply it by 100. And that is all that it is. It really is that simple. And it's just trying to talk about precision in a metric that doesn't have, it's not specific to how the variable is measured, right? So it's a unitless measure.
Can I ask a question?
Yes.
Oh. Jesus, I just went blank. Sorry, I'll get back to you now.
Okay. Okay. When you think of it, let me know. Okay. So we're going to move on and we're going to talk about the analysis of subpopulations. And this is a very important topic because this is one of the places where the analysis of weighted data is very different from the analysis of unweighted data.
Christine, sorry,
So-
someone wanted to know how to do number 3 of the exercise.
Oh, okay, well, that requires me to go back and see what number 3 was. Survey tab, SVY, tab, age group, comma, OBS, space count. Okay, subpopulations. When you have unweighted data from an experiment or from a quasi-experiment, something like that, let us say that you're only interested in analyzing the females. Well, you can just delete all the data from the males. If you're interested in analyzing only the folks who are over age 50, you can just go ahead and delete out all of the data for those folks who are under age 50. That is not true when the data are weighted, and there's 2 good reasons for that. First of all, remember what I said about your sampling weight. If you sum down the sampling weight, if you add up all the numbers in that column, you should get a very good estimate of the number of people in the population. Well, that cannot be true if you just go start deleting out cases, right? The second thing is that the way the math for a subpopulation works is that the cases that are in the subpopulation, and I'll tell you how to define that in just a second, but the cases that are in the subpopulation are used to calculate the point estimate. All of the cases are used for the calculation of that standard error. So all of the cases have to be available for you to correctly calculate your standard error. Well, you just went through all of the effort to identify what kind of sampling plan you had, find the right variables, write the survey set command correctly. Don't go wasting all of that good effort by deleting out unwanted cases. Okay, and so leave all the cases in. And when you want to analyze a certain subpopulation, like only the females, only the people over 50, only the people who, you know, have this diagnosis or are not pregnant, whatever it is, you have a couple of options. What I typically do is I create a 0-1 variable. I use the generate command, right? I shorten it to gen, and I say gen, and I give it a name, and then I say equals 0. And then on my next line, I say replace this new variable name equals 1 if, and then I go put in all my subpop specifications. So now it's 0 if you're not in my subpopulation, 1 if you are, and now I'm ready to rock and roll. Okay. By is also a problem because the by prefix doesn't let Stata see observations in other groups formed by that by variable when it's processing within a certain level. So for example, if I have a 3-level variable and it's coded 1, 2, 3, and I'm getting the mean of age for group 1, group 2, and group 3, when I'm calculating the group, the mean for group 1, I can't see the observations in 2 and 3. When I'm calculating the mean in group 2, I can't see 1 and 3. So you usually don't use by with the weighted data because, again, you're going to have a problem in calculating that standard error. There is a excellent discussion of what this whole topic is known as conditional versus unconditional subdomains. Brady West made, well, he's a PhD now, but he was only a grad student, only a graduate student. The guy's totally brilliant, but he had a Stata presentation in 2009, and he went through all the whys and wherefores on this. So I'm not going to go into the details there, but if you want an excellent readable discussion of that, I linked his presentation there. What does Stata offer to allow you to do this? They give you two things. There's a subpop option and an over option. The subpop is kind of like, I only kind of liken it to deleting cases. It doesn't really delete them, but it only gives you the output for the requested subdomain or the subpop. Domain, subdomain, and subpopulation are all used interchangeably. It all has to do with where you're working, because sometimes when they're talking about a physical location, they'll call them domains instead of subpopulations, because it's literally a place. The words all mean the same thing. The over option is used when you want to get the estimates for each of the levels of your categorical variable. So we're going to look at examples of both of these, and you can actually use them together, which is super cool too. Let's see here. We already covered why you can't just delete cases, because your sampling weights won't add up correctly, and because your standard errors will be wrong. If you want more information about this, I've got some references here, and then in the Stata 17 manual, you can look on pages 67 through 72. They go over the analysis of subdomain subpops. All right, so let's get into this. You can use an if within the subpop. I know that's super confusing. You can use the if within the subpop. Remember though that it treats it like Stata treats any binary variable. So it's 0 and not 0 or not missing. So if you have the variable coded 1, 2, everybody will be in the subpop because it only says 0 is not in the subpop, 1 is in the subpop. And actually you should never be missing on a subpop variable. So just keep that in mind, because some software programs will actually error if it finds a missing on the subpop variable. Alrighty, so I usually do create a variable, a binary variable. We are just going to use some binary variables that are already in the data set. Okay, survey mean age. Okay, we've seen this command. We know this output should be comfortable here. Subpop is an option on the SVY prefix. So the comma to indicate that it is an option, you say subpop parens, and I can just say female here because this is 0, 1. So this here, this estimate is for the members of the population that are coded 1 on this variable. In practical terms, that means the females, right? So we see in our output here, this is our raw number of observations in the data set, the estimated population size. Here are the 2 new lines here. We see the number of observations in the subpop. This is the raw n, and this is the weighted n. So the 5,428 participants, female participants in the survey represent 60,901,624 people in our population. Here's an example using if in the subpop specification. There are numerous ways I could have written this. I chose this way. Just going to have to choose one of the ways. Bang equal is not equal. If female does not equal 1. I could also have written equal equals 0 and gotten exactly the same thing, right? It doesn't matter. You can do it either way. And we see here, this is the average age for the men. So what we see here is that the average for the females is higher than the average for the males. We see the estimated number of males in our population to be this 56,122,035, and these 4,909 fellas were the actual participants in the research. Okay, so these are different ways of specifying the subpop. We can also use over. You get the same results, but notice now I get the mean for each level of the variable female. And so when you're using a categorical variable here and you want it for the different levels, well, this is an easy way to get this. Now, as you can see, you can put multiple categorical variables in this over option here. So when I do this, this is how you rated your health. If you rated it as excellent, fair, average, poor, good, whatever you rated it, right? And then your female. So here, this is the mean for the people who said poor health and are coded as male. The folks who said poor health and female. Down here, we have the people who said, I have excellent health and I'm female. So every combination of these variables gets listed out here. And so that's good. You can put it all together if you want, right? If you need to. So now I'm only looking at the females for the mean of copper for every combination of race and region. This race variable has been recoded so that it's white, black, and other. It's got 3 levels, and then I think region has, I guess it was 4 or 5 levels. So here we go. This 4,768 is the raw number of females, our estimated population size for this. And here are our averages for the females for each combination of race and region. All right, sometimes, and I had an example of this in in my other one, but I was using a data set that I created, and so people couldn't follow along using the same data set. But it had an excellent example where I couldn't get a standard error. So I'd get a mean, and then I'd just get dots, and you had to do a little bit of detective work. And what had happened was, so we use E-stat size to get the number of observations and then the weighted size. Well, look down here, we have a 6 and we have an 8 these are for others in the Northeast and Midwest. And you notice here that your standard errors are relatively large compared to the widths of the other confidence intervals here, right? These standard errors are large, these confidence intervals are wide, and that's because the raw N has gotten to be so low. In my other example, we didn't have any of these values. We looked at this, we said, oh my gosh, we have only about 5 observations. And it turned out that all 5 observations had exactly the same value. They had given the same rating on whatever it was, health or something. And that's why there was no standard error given. But when you see this in your output, you may need to do a little bit of detective work to find out why that is the case. And this E-stat size thing here is now super helpful to identify, hey, wait a minute, some of these things are getting down to a very low number of respondents here. And that's why I was saying that sometimes this is really a very, very helpful command. All right, so you've got all these things. And you might say, well, gee whiz, I wonder if there's a difference between these two numbers. I wonder if these two numbers are statistically significantly different. Okay, it's a legitimate question to ask. You can do that if you want. We're going to take it as a slightly simpler example, and we're going to ask, is the difference in mean iron different for the males and the females? So I've used over here so I get both of these numbers. And what I really could do is just subtract them, and I would get that difference. But I wouldn't get the standard error, and because I didn't get the standard error, I couldn't actually do the test. So I want Stata to do this for me so that Stata can calculate the standard error, because that's why we have software, make it do the hard work. So I need to know what Stata calls these numbers. It's got a label that hides behind them that Stata sees. And I can get Stata to tell me that if I use this option called Coef Legend. And we're going to use this option a number of times throughout the workshop. And it works very well for both weighted and unweighted data. All sorts of commands use this. So I do this, and instead of getting my standard error and test statistics and confidence intervals, I get these labels. Now, they're kind of persnickety, you know, I wouldn't want to retype this. I literally copy and paste them out of my output into my do file. That is how I do it. So I don't make a typo, because Stata is not forgiving about those typos. But what I have done is I literally copied and pasted this from here. I wrote lincom. Lincom is short for linear combination. Put it here. I put a minus sign, and I copied and pasted this one here. And Stata dutifully did the subtraction for me, right? You can look at those numbers and guess, yeah, 7.5. Yeah, that's about what the difference is. But the magic is that Stata calculated the standard error for me. And it can do that because it remembers all the output here. And that's why I needed the label instead of just the numbers, because I needed Stata to remember this stuff so it could calculate the standard error for me. This number divided by that number is this number here, right? And so now I can say that, yes, there is a statistically significant difference in the average iron in males and females, okay? And here I'm just using the display command to say, yeah, I could do this myself. I get a little bit of rounding error, I get the same number. But again, my problem is I don't have a standard error. And because I don't have a standard error, I can't get the rest of this output that I really want. And so I let lincom do it for me. And there we go. Slightly more complicated example of the same thing. So I'm going to kind of blow through this, and I am actually starting to lose my voice, which is why I keep pausing to drink water. Sorry if that's annoying. we're going to go over region. We'll get the mean of copper. We can use our coef legend option, and now we can use lincom to do any of the comparisons that we would like to do. I will show you other ways to do multiple comparisons, including ways to start to correct for multiple comparisons. But when you just need to do a couple of them, this is a perfectly legitimate and super easy way to do those kinds of comparisons. Finishing out this section, we have the survey total command. Again, I couldn't find a good variable in this data set to show what I needed to show here. So I'm just going to tell you why all the rest of this stuff is here. Survey total, of course, gives you the total of something. I just use diabetes, you use whatever it is that you do. But typically the total is really, really, really big, and Stata has to exponentiate it. But like I said, the exponentiated value doesn't do you any good when you're actually trying to write up a manuscript. So there's a couple of ways to get Stata to give you the actual underlying numeric value, and that's what you really want. And so estimates table is one thing. This is the B, or the coefficient, and this is the format that I asked Stata to use. SE is obviously the standard error, and this is the format that I used. I use different formats only to show you that you don't have to use the same one. You know, you can use the same one. It doesn't make any difference. I'm just trying to show that you don't have to, but that's a good way to get Stata to expand that out for you, so you have the full number. I run it again. Mat list is another way. Again, I use a format option to get that number out so that I can see it. And then the only point here is that I can use the over option. And then when I do estimates table, I get the estimates and standard errors for all the different categories there. Okay, so that was a lot. We've gone through that section. The graphing section is actually pretty short, and then we move into regression analyses. I have some more exercises for folks to do if you're interested. Does anybody have any questions at this time?
Yes.
Yes.
What about normality? Do we ever test if variables are normally distributed in survey data or not?
Test, no. Look at the distribution of, oh yes, and I will be getting to that shortly. You're just about 10 minutes ahead of me, so I will get there very shortly. That's a great question. It is an issue, and I will show you how to look at distributions. Any other questions? Okay. If anybody wants to do exercises, we have exercises for subpops. You can calculate the mean of albumin for females for all age groups, and then just for the males ages 20 to 29. I will put those in the chat as well. And if you have any questions while we're doing these exercises, again, we'll only take 2 or 3 minutes to do this so we can keep moving on. Go ahead and ask me. Stop my share, go to this. And now the 3 things are in the chat. Any other questions? Okay, well, I am going to take a short break, and I will be back in about a minute, minute and a half. All right. Is everybody done with the exercises or done with whatever they wish to do? And are we ready to go on? Are there any questions that you'd like to ask before we continue?
Can we go over number 3?
Number 3. So it will be S of V Y, comma, space, subpop, open parens, female, equal 1, close parens, colon, mean albumin. Wait, go back to the subpop. So it's subpop if female equal 1, ampersand, age GRP equal 1, close paren, colon, mean albumin.
So Christina, in our data set, we don't have age group. Is that something you imported from the EXPT file or something like that?
No, I have this variable here. You don't have, it didn't come in.
Oh, I see. It's not GROUP.
No, it's this. This is age group right there.
Let's see.
So the command would look, what did I say? SVY, whoops, comma, sub, spell correctly here. If female equal 0, ampersand, age GRP equal 1, whoops, spell albumin correctly, look like that. Does that make sense to folks, what I did? So I said if female equal 0, which is the males, and then the youngest age group is 1. Okay, so. All right, let's go on and talk about graphing. Okay, graphing is something that's another fairly recent development in survey stuff that you can actually get weighted graphs. Now, some graphs allow for the p weight to be specified and other graphs don't. And this is where we'll have the very, very brief talk about the fact that Stata allows for different kinds of weights. Specifically, it allows for a frequency weight, a sampling weight, an analytic weight, and an importance weight. Importance weights are pretty much undefined and rarely used, so let's just forget about them. We've covered what a sampling weight is, so we can set that aside. We're going to use the frequency weight here, and we're going to use the analysis weight in a couple of minutes, so let's go over what those things are. Frequency weight actually comes from ages and ages ago when data sets just couldn't be too large because storage space was at a premium. We were using floppy disks or cards to input data. And so you just couldn't have these huge data sets. And so what they said was, look, I've got 5 observations that are exactly the same, and I have 10 observations that are exactly the same. And so what I'm going to do is I'm going to put 1 observation in and give it a weight of 5, and that's going to tell the algorithm to pretend that there are 5 of these that are exactly the same. And the next one I put in that pattern, and I'm going to put in a frequency weight of 10 and say those are exactly the same. So expand it out. So I put in 2 rows of data to account for 15 observations. That's the idea behind a frequency weight. It's really very different than the sampling weight, but we needed a bit of a hack because the histogram command will only take a frequency weight and we have a sampling weight. And so the suggestion from Steve Brady and Pat in their book, which was Applied Survey Data Analysis, 2nd edition by Stephen Haringa, Brady West, and Patricia Berglund, it's the second edition, it's the 2010 edition. They have this suggestion in there is just take the integer part of the sampling weight and use it as a frequency weight. It is a hack, to be sure, but the reason it works is because in a histogram, you don't get a standard error. And that's why this is an okay thing to do. This is the only time I would ever do this. I would never do this for any other reason, but in this situation, it works. And this gives me a weighted histogram of this variable. And the weighted histograms I find to be very, very useful because I need to know the distribution of things. In a moment, we're going to talk about how to get a correlation. And a lot of the variables that you'll find in the data sets, especially NHANES and CPS, they are crazy, crazy, crazy skewed. And you want to know that before you go running something like a correlation where you're assuming that the variables are approximately sort of normally distributed, okay? Because they're just not. If you want to add a normal overlay, a normal curve, you just use the normal option like you normally would. And there you go. Age here, not normally distributed, that's okay. Oh, one thing I did want to point out, normally when you use NHANES data and you get a histogram of age, it looks like this. And you see this crazy huge spike out here. And that's because in NHANES 3 and in continuous NHANES, the data are top coded at 80, which means that no matter what your age was, if you were age 80, 81, 82, 83, up to whatever, you got a code of 80 for your age. And that's why you have this great big old spike here. The reason they do that is, again, part of the statistical disclosure control. They're trying to protect the identities of these people because, as you know, there's just fewer and fewer people of a particular age as that age increases, right? There are fewer and fewer people who live to be 100, live to be 105, live to be 110. And so they don't want to provide those exact ages because it might allow somebody to go figure out who a respondent is. And so to help protect the identity of those folks who are in this category, they just top coded at 80. And so you see this crazy spike here. And this is very common in NHANES data. And so I just bring that up because it does surprise people if you don't know to expect that. Like I said, they've really sanitized this data set, and this is NHANES too, so it's top coded somewhere else anyhow. Okay, the box plot command will respect p weight. I shortened it to PW here. You can make box plots. You can use by to make your box plots. Honestly, the truth of the matter is I never see anybody use a box plot once they get out of a class. I don't see these in papers or anything, but you should remember here that this here is a median, not a mean. And so I show you the mean here. And then I show you a hack way to get the median. So if you need to report what the median is to go with your box plot, you can do this. This is based on a fact that's on the Stata website. And notice here that we're using the A weight or the analytic weight. So you will see every once in a while, people bop around between an analytic weight and a sampling weight. So that they switch from an A weight to a P weight and a P weight to an A weight. There is a good explanation of the math behind this and why you can do this in the third edition of Hawkes's multi-level book. But here's the important part that you need to keep in mind. The math for calculating the point estimate when you're using a sampling weight and an analytic weight is the same. The math to get the standard error is actually different. So when I only need a point estimate, in this case, my median, I can switch between an A weight and a P weight and I'm okay. If this had reported a standard error, it would not be the correct standard error. So but you will see a couple of places where all of a sudden they've switched to an A weight and people are like, wait, how can you do that? And it's because the math for the point estimate is the same, but the math for the standard error is actually different. So that's what that is there. So I put the correlation part here right after the graphing, because when you go to do the correlations, you will find that a lot of the variables are really, really skewed, and you're going to have to think twice about doing the correlation. There is no convenience command in Stata 17 to get correlations. I believe there is one in the survey package in R, and there is one in the current version of Sudan, but it is not in Stata and it is not in SAS. There are at least 3 hack ways to get a correlation, a weighted correlation in Stata. I'm going to give you my favorite way, because my favorite way, even though it is really, really unintuitive, I completely admit to that, I get the standard error, and honestly, that's usually what I want out of this, is my standard error. And the other ways don't give me that standard error. So what I am using here is SVY. I'm using the sum command. Do not panic. You can use the sum command for a lot of things other than a structural equation model. SEM is for structural equation model. You can use this command for many, many other things, and I am using it for another purpose. I am not running a structural equation model here. I do need my parens. I have this little arrow, which is the, whatever you call that, the little wedgie bracket thingy, dash, and then the 2 variables that I want for my correlation. And the most important part is the standardized option. And what we are working with here is this bottom line, which is the covariance between the 2 variables. And if you remember, a standardized covariance is a correlation, and that's the fact that we're working on, is that a standardized covariance is a correlation. So this here is my correlation coefficient, and this is its standard error, my test statistic, and my p-value. And of course, now I get my standard errors, or excuse me, my confidence intervals, which I want. Now, there's another thing that you need to keep in mind besides the distribution of the variables that you're working with. And that is, again, we are really, really, really overpowered. This correlation coefficient is statistically significant, but it's approximately 0.03. So my question to you is, does a correlation of 0.03 matter in the real world? Maybe it does, maybe it doesn't. It is not a question that just can be answered. It's specific to your research situation. And so when you get these correlations, statistical significance, you know, is easy to get because you've got so much power. It's time to set that aside and say, does that correlation coefficient matter in the real world? And that is the question that you need to ask yourself. Here we do the correlation between the systolic and diastolic blood pressure. No surprise that it's approximately 0.7. And again, it's very accurately estimated. You can see the small standard error and the narrow confidence interval. The graphic representation of a correlation is, of course, the scatter plot. So let's see here. We are going to do that right here. We use the 2-way. We say scatter. These parens like this is the way to overlay the graph. So this is the scatter plot here. This is the L-fit, which is putting in this red fit line here. Both of these respect a p-weight or a sampling weight here. And so I say, here's my scatter plot. Here's my fit line, and there we go. This is what we get. So this is the weighted graph. there's all sorts of ways to make this graph look better. Sometimes I have these as open circles instead of the closed one, so it doesn't look like the blob, like a Rorschach test on your graph, because to me it kind of looks a little bit like a Rorschach test with this kind of thing going through it. I don't know, but at any rate, that's how you can do your correlation. This is how you can get the graph of it. Now, one of the other things I had up here is, let me see here, can I get over to that? There we go. So I'm working on a paper using NHANES data, using a bunch of the variables, and this is a very typical distribution that I see. So all of my observations are over here, and then I've got this really crazy long right tail, and the last data point is actually way out here past 1,000. And so I have to go to the people with the substantive knowledge and say, is this even plausible? What do you want to do about this? Do we want to subpop some of this out? What do we want to do here? Because, you know, this is going to be a difficult distribution to work with, even for basic things. So that weighted histogram that I showed you is often very, very useful, not because I make assumptions about an outcome variable or something, but I need to know if something's going to have a long right tail like that, because among other things, it really can cause some serious estimation problems. So we've got that. Let's do a few more descriptives with categorical variables, and then we are going to move on to some regressions. We've seen survey tab here. The default output is proportion. We've seen the proportion command. Obviously, you get proportions. Here's some more examples with the tabulate, using the count option and expanding the cell size so that we get non-exponentiated numbers here. You can use up to 5 options, but the confidence interval option takes up 2 of them, because really what Stata is saying, I've only got so many columns I can put output in, and so you tell me what you want in your columns. However, the order of the observations doesn't matter for the order of the output. So here I use the SE option so I can get that. Here I use some other options here, and you know, you can do whatever it is that's going to suit your purpose. The only point here was to show you some examples of options that you could use if you find them to be useful. Survey proportion with the over for subpops here. Here you can use COAF legend if you want, and then use lincom to do comparisons if that's helpful for you. So the only point of this section is to show off options and show how you can mix and match these different things to get whatever it is that you need to do. This should not be seen as a to-do list. I need to do this and this and this. Instead, you should think of this as more of a buffet. You come up, you say, hey, I need this, I want this, a little bit of that, some of this, and you make whatever, you take whatever you need to do the analysis you need to do, right? And so all I'm trying to do here is show you how you can mix and match these things to get done whatever your task at hand is. All right, graphs with categorical variables. The bar command respects p-weight, but it does want both variables, male and female. So generate male equals not female. Okay, that's just a quick way to do that. Now we have the mean of male and female. It's not the most exciting graph I've ever seen here. We did the mean over this so that you can see the numbers, and then you can see this. If you add some extra code out here, I think you can actually get the numbers put out here. Again, just different ways to create whatever graphs are informative for your purpose here. Bar graph, if you want to have it vertical instead of horizontal. Use the p-weight, here's your over, and this output here, these numbers all look the same, which is why your bars are all of the same height here, because this is your 42, 41, 42, well, 41.97, which is kind of 42. All right, that was what you have available for graphing in Stata with weighted data. We are going to move on into various kinds of regression at this point, unless there are any questions that I can answer at this time.
I have a question, Christine.
Yes.
Is there a way to get like a error bar with those graphs in survey weighted data?
You know, I've never tried to do that. I have actually never tried that. That is a good question. I'll have to look into that. I don't know. Send an email to IdriStat and just say I'm the one who asked about error bars on a weighted bar graph. And if I can find something, I'll send it to you. I'll respond and send it to you. That's a good question. I've never thought of that. Thank you for asking. That's cool. Any other questions?
Yeah, hi, a quick question.
Yes.
I'm wondering if there's anything to keep in mind if we're also working with multiple imputation for missing values as at the same time.
There's so many things to keep in mind. Ouch. I cover weighted MI in the advanced survey data analysis workshop. If you're the person doing the multiple imputation, then there's a lot to keep in mind. And I have to say that the literature on that really hasn't settled on how you're supposed to do it. I have seen all sorts of different suggestions, and they all tend to be very situation specific. I have not seen anything that is really a general way to do that. I know that one of the NHANES data sets, I think it was NHANES 3, experimented with putting out 5 imputed data sets, and they backed off on that. And I don't think they will ever do it again because they found it to be a disclosure nightmare. If you have 5 imputed data sets, that gave people far more information to try and track down individuals. So I don't expect to see a lot of that from the distributors of the public use data sets. If you're the one trying to do the imputation, my suggestion would be that you really do need to take into account the weighting, at least the weighting, probably the PSU and everything else with it as you're doing the imputation. The other real hard part about that, though, is that these data sets already tend to be large, and doing even 5 imputations, which is usually never enough, but even doing that can be a lot for some desktop machines to handle. The other real problem, though, is that the variables that you would want to use in your multiple imputation model are typically not released with the public use data set because they represent a problem for re-identification of the respondents. And so I always kind of cringe at that idea, because the quality of the MI model is super important. If it's a bad model, you can actually do more harm than good. You can introduce more bias than you take out, but you are definitely confined to the variables that are in the data set, many of which are not included, or they have been, say, modified in some way. Like we saw, age is top coded, other things are bottom coded. Extreme values are sometimes set to missing. Even if they did have a valid value, they will set them out to missing. And that is not documented anywhere. And that's on purpose. They don't want the end user to know that. But all of that combines to make multiple imputation a real challenge for the end user. And I don't mean to be grim about it, but it really is a heck of an undertaking, I'm sorry to say. Now, if you are running a linear model and strictly a linear model, you can run that through the sum command with the survey option and use method, was it MVML? It's one of those combinations of letters. And it will do that kind of correction for you. And so that is often what I suggest if you've got a linear model. Does that help? Does that get you what you wanted to know?
Yeah, I think it sets me in the right direction. And just
Okay.
you said the workshop is the advanced one on imputation, that there's also some notes about this.
Yeah, it's my advanced survey data analysis. I don't have code on there because I hopscotched through 4 or 5 software packages because there's no one software package that does everything. Obviously, that's why we have all the different software packages. But I really struggled with that one because I don't want to be explaining M+ code when half my audience doesn't even know what M+ is. And I don't want to be explaining Sudan code when you don't have a Sudan license. And I don't want to be explaining Stata code if you're a SAS user. So I kind of struggled with that one, but I do go over a bunch of the whys and wherefores and what to be careful of. And there's a bunch of references, but as I said, that literature is particularly unsettled. And so you will find all sorts of contradictory references, which of course just takes it to a whole new level of difficulty. So I'm sorry, I don't have anything really great to offer you there, other than to tell you that it's still very much a work in progress.
Well, thank you very much.
Okay. Moving on, let's get through some regression. We're going to go through OLS regression to begin with here. There's a lot of nice things to know and love about OLS regression, or regression in general with weighted data. The upsides are that the commands work exactly the way that you expect them to. You use the SVY prefix, you say regress, you give your outcome, you list your predictors. If they're categorical, you put IDOT, you press enter at the end of that and it runs it. Your output looks very familiar, and all of the output is interpreted just like you would out of any other OLS regression. So you sing your same favorite song, you know, for a 1 unit increase in my predictor, my outcome is expected to change by whatever the coefficient is, holding all other variables in the model constant. It's all the same. A lot of the post-estimation commands that you know and love and you come to Stata to use work the same way as well. You have margins, you have margins plot, you know, which is, you know, the goals, you know, that's what you want. Contrast works, PW compare, all of those post-estimation commands that you rely on in Stata, they all work and all work the same way. So there's really nothing new to learn. Coef legend works, lincom works, it's all beautiful. One thing I want to make sure that I get in here before I forget. If you use a subpopulation on the SVY for the regress, you're going to have to turn around and use SVY, the subpop in the option on margins if you're going to use margins. So let me give you an example of that, because I don't think I put it in the actual, let me see here. So let us come here and I am going to say subpop, whoops, what do I have here? Rural. I'll subpop it on rural. Okay, and I go ahead and I run that. Now, when I say margins, I'm going to say margins female, right? And then I'm going to say spell it correct, VCE unconditional. I've got a big note on that on the web page, and then I'm going to say subpop rural. Now, I bring this up because I had a very long email conversation with the good folks at Stata Tech Support. And what I thought was that if I had subpopped it here on the regress command, this margins would just be for the subpop, and I was wrong. Without this option, this is the margins for the full sample, right? So I have this here, I need to have this here, and this is the only post-estimation command where I have to do that. But I did want to make sure that that was super clear. This VCE unconditional here is used almost always when you have a Taylor series linearization for the variance estimation, which means whenever you have a PSU strata, you use this. You don't use it with the replicate weights, but you use it here. And let's see here, the web page has this here. It specifies that the covariates are not fixed and are treated to be treated as if they've been sampled. So you almost always use VCE unconditional. And if you had a subpop on the regression, you probably want the subpop option on margins. And again, it is specified out here like this. Okay, this whole part of this here is like 3 different ways to do a t-test in Stata with weighted data. There is not a weighted version of the t-test command. There's no convenience command. We call them convenience commands for doing that. But there's all sorts of different ways of doing it. This first way is to recognize that a t-test is actually just a linear regression with a single binary predictor, and you can go forth from there. So this is the mean for the group coded 0, and this is the difference here. And since you're testing here that this difference is equal to 0, that really is the t-test right then and there. We used margins with VCE unconditional. This number here is this number here. Our males are the ones who are coded 0. That's why they are the constant. The difference between here is approximately 26, and hence that's the 26 that you see there. And I just did the math there. We're going to use LinCom to look at that difference. So we have our margins here, just like we did above. Here I have to use post because margins is a post estimation command to regress. And so if I want to capture the stuff out of margins, I have to post those results. So those are what Stata is holding in memory. So I go ahead and do that. This is what your output looks like. Again, I simply copy and paste my 2 labels here. I subtract them. There is my 26, 26, the same t-value, the same p-value, everything is the same. So that was a long-winded way to say, hey, you can do a t-test. And if you need to show yourself that it really is those 2 things, then use LinCom. You can do the same thing with the over option and just using mean and do the subtraction there. And so again, way too many ways to show you how to do a t-test. All right. Like I said before, you can go ahead and use the regress command with the survey prefix, just like you would without the SVY prefix. I've put in a covariate age here. So that copper is my outcome.
Christine, quick question.
Yeah.
Is there a way to directly do a t-test using survey?
That's what I just, no.
So you can't test it against like a known value. Like if you want to test the mean.
Oh, you mean like a
5.
1 sample t-test?
Yes.
A 1 sample t-test. I have never actually seen that done in Stata. I might be able to get it out of Lincom, but there is no built-in command. The only place I've ever seen a built-in command for that, I think, was Thomas Lumley's survey package in R.
Okay.
But no, honestly, I don't see too many t-tests like that, though. Usually it's a two-group thing.
Yeah, I see.
Okay.
Thank you.
But thank you for that question. I actually think you can do it out of Lincom. That's how I would try it. Okay, we added in a covariate. Yes, this is where we are. The output looks like exactly what you would think. We have our 31 strata, our 62 PSUs. That's where this design degrees of freedom comes from here. Our unweighted number of observations, weighted number of observations. This is the overall test of the model. It is statistically significant. And this is the R squared. This is the population R squared, or what you might know as the adjusted R squared. Okay, so think of this as your adjusted R squared. So we're saying that approximately 15% of the variance in the outcome variable copper is accounted for by our predictors female and age. We can see that female is statistically significant. We found one of the very few instances when a variable is not statistically significant. We can use the margins command to get the predicted values, the predicted means for males and females with respect to copper. Any other post-estimation commands that you find useful can be used here. Let's see here, you can do the interaction terms here. So again, the pound, the first pound includes the interaction term. The second pound includes the lower order effects, which you do want to include. And so we can come down here and see our interaction term right there. We can use the contrast command for the interaction. And since that was a 1 degree of freedom test, this isn't exactly a hot news flash that it's statistically significant. This number is this number with a bit, there's rounding here, that the same numbers. T squared is F. So if we've had some reviewers say, I want an F instead of a T. Okay, square the T. So there's that. But if you use the effects here, you can actually get the contrast here, which of course is the same thing as your coefficient and its standard error. Just showing you options that you can use that may be helpful to you in some situations. Here we get the adjusted means or estimated marginal means, least squares means, whatever you want to call them, for your 4 categories of female and diabetes here. And then margins plot can be used to go ahead and graph the interaction term. This is difference in differences. The binary by binary interaction is called difference in differences. Sometimes I see it as capital DID. So if that's something of interest to you, I did work through this here. The interaction term is the difference in this difference, male, no diabetes, minus male, yes diabetes, minus the quantity, female, no diabetes, minus female, yes diabetes. So you can run margins with coef legends and post, and then actually do the subtraction with Lincom. So I went ahead and did that. Here we go. And now we've got this, and we see it was exactly the same thing that we saw above here. And then you can, if you want to look at the difference in these values here versus these values here, again, Lincom is your friend here, and you can just do the subtraction. You can see that for males, it is statistically significant. For the females, it is not. And that's because when you look at this graph, those two numbers are the same number. So again, this is just showing you what you have available to you. This isn't saying, you know, this is what you have to do. It's just saying these are things that you can do. Here we are. So we have a categorical by continuous interaction here. Not that there's anything magical here, just showing you that you can use dy dx if that is your preference. You certainly can. And then you can use at if you prefer to do it at specific values instead. You get this. Either way, you can use margins plot and get the graphs. So I don't really feel the need to go through all of this output and explain it because it's all the same as in the non-weighted situation. I would rather spend my time though going over some of the places where survey data are different from non-survey data. Just another margins plot with some options there. If you want to do your confidence intervals like that, you most certainly can. Okay, where are things different? Things are different when it comes to regression diagnostics. That's where it's really, really different. And the reason it's different there is that for the most part, the regression diagnostics have not been worked out yet. I do know that several big names in the field have grants that they are using to work on this topic. They've certainly been working on it for a while. It is not an easy thing. I never worry about normality when the sample size is this large. Not that I usually worry about normality of the residuals, but definitely don't worry about that. The independence issue should have been taken care of by specifying the sampling plan and such as that. But you definitely worry about things like the homogeneity assumption and making sure that that is met. At this time, I don't have a great way for you to assess that, but that is one of the areas of concern. Model specification, so you always assume that the model is properly specified. Again, that's a bit dicey with the survey data because you have no control over what variables are included in your data set, and you are not in control of how they got coded, whether they deleted out extreme values, they top coded something, bottom coded it, whatever they did, you don't have any say in that matter. And so having a properly specified model is in some ways a little more difficult than it would be if you had control over the data collection yourself. So that is one place where things are really quite different here. Showing off the use of the contrast command for the multi-degree of freedom test, you know, there's nothing different there. PW compare works. You can, there's not a lot of options available with the survey data. I think it's CDAC and Bonferroni and maybe one more, but that's about it. Just showing you some options that you can use so that you can do this. In logistic regression, you have the same concerns that you would in unweighted data. They just might be a little more pressing here. So one of the things I always tell people to do is start with the tab command for your outcome measure here. This is high BP. This is a derived variable that Stata already had in the data set. And I'm looking at the proportions. Sometimes the proportions can get to be very lopsided, and this looks fine. I'm not worried about that. And I've got a reasonable number of raw observations in both groups of my outcome. And so that makes me feel good. I do a cross tab between my predictor and my outcome just to make sure that I've got approximately sort of enough observations in each of my groups. Now, as you look at this table, in most situations, I would have, this is the raw count down here. You can see the key down here, that bottom numbers, the number of observations. 310, 419, I'm thinking, you know, for most situations, that's really not bad, but you can see here that it's a small percentage of the population here. And so while I'm not really worried about estimation problems, I am expecting that my standard errors are going to be larger for this category than for some of these other categories where the ends are much larger. So I go ahead and run my logistic regression. I have changed my reference group to be 3. The default is to use the lowest numbered lowest numbered category as the reference group. I have chosen to use 3, which I think is thought it was good. I guess it's not. What is that? Oh, average. It's average. So average is my reference here. Now looking over at here, you can't just get a sense right away if the overall variable is statistically significant or not. So I go ahead and use the contrast command, and I would report this 4 degree of freedom test saying that, you know, taken together, the omnibus test of health is statistically significant when 4 degrees of freedom. Here's my F, here's my P, and then these are the specific comparisons to average. And you, of course, can use margins to get the predicted probabilities if that would be helpful to you. All right, here we go with the categorical by continuous interactions here. Again, I use the contrast command to get the multi-degree of freedom test. It is not statistically significant if that's important. But I can get my predicted probabilities, which I see here, and then I go ahead and graph them here. Oh, here's another important thing that I do want to point out. With logistic regression, a lot of people want to report the goodness of fit test. There is a goodness of fit test. It's the Archer-Lemischau test, which is a modification of the Hosmer-Lemischau test. Now, I will say that even Hosmer himself has said that, you know, he's not so in love with this test anymore, but I do still see reviewers requesting it. The important thing to remember is that it is not available if you run your model with a subpop. Okay. It just mathematically, it doesn't work. And the last time I tried it, it didn't error. And that really concerned me because you got the wrong answer. And I did ask Stata tech support to change that so that it would error. And I haven't checked to see if they did that, but that's the issue there. So you can use it if you've run a logistic regression, but only if you ran the logistic regression on the whole population, not if you ran it on a subpop. And so if a reviewer asks you for this on a subpop, you can say that doesn't exist yet. I've had reviewers ask for things that don't exist yet. I'm like, oh, I love that comment. So here we are, EStat, GOF, and not statistically significant. Ordered ordinal logistic regression, survey O-logit does work, blah, blah. I'm not going to go through this, but the important part is that, as you know, with an ordinal logistic, you want to test the proportional odds assumption. So what you're doing is you're assuming that the odds that are calculated in each set of the equations are the same, that it's reasonable to constrain them to be the same. And that is a wallop of an assumption there. And so here you're just getting the odds ratios here. But there is none of the built-in commands that you would have used with unweighted data. Let's see, was it O-logit and Brandt? no, O model and Brandt, they're not available here. Steve Brady and Pat in their book here say that you can use the community contributed command gologit2 to try to assess this assumption. And I've adapted their example to work with this data set. So what I did here is I used the tab command for this variable with the gen option to create the dummy variables, because I have to do this. I can't use the IDOT with what I'm about to do here. gologit2 will respect IDOT, but the test commands afterwards need it out like this. And so although this is a community contributed command, it does respect SVY. That part's good. You get all this stuff. And then what you end up doing is doing test for each of the variables using each of the different equations. And so it is really long and really, really, really drawn out. And you're hoping pretty much that these are not statistically significant, because statistically significant means you're violating the assumptions, and for a fair number of them you are. So in totality, I would say that you probably did violate the proportional odds assumption when you ran this model here. You probably want to go modify the model or do something different here. I probably would have just used gologit2 instead of ologit. Gologit is a generalized ordinal logistics, so it relaxes that assumption of proportional odds. Definitely read more about it if that's something that is pertinent to the work that you're doing. But what I wanted to include in here was this way to try and test the proportional odds assumption. And as you can see, it's just kind of a lot of tedious code to write out. So that is all I really wanted to say about ordinal logistic, because all the rest of it is just like the unweighted situation. The interesting thing about multinomial logistic here is that this is one of the places where you can run out of degrees of freedom. And so I liked my previous example in my other data set. I couldn't replicate all the problems in this data set, but I will tell you where they are likely to occur. Now, I use this table command here instead of survey tab because I want to use 3 variables, and survey tab, well, tab will only let you use 2. So table will let you use 3. And what I'm doing is I'm checking, I'm checking my ends, and you can see some of the ends get to be very, very small indeed. We'll want to keep an eye on that, make sure we don't have estimation problems. But that's what the point here was, is just to check my raw ends. The mlogit command runs just like you expect it to. You just put the SVY in front of it and call it a good day. And then you get your series of equations here. And if you use the RRR option, you can get relative risk ratios. And then you can change the base category if you want. That's what this is. And then I put in the interaction. Now, in my other example, what had happened was I ran out of degrees of freedom, and I got a dot here and a dot here. So it wasn't able to calculate the overall test. So in the stated documentation, they do cover this situation. And what they say is that your point estimates are properly calculated, but you need to be suspicious of your standard errors. If you're suspicious of your standard errors, that means you're suspicious of all of these values here, right? Because all of these values are based on this standard error. And that's why the standard error is so important, because that's telling you about all the rest of this that you usually care about. And so the idea is that you're assuming when you calculate these standard errors that you have lots of lots well, not observations, but lots of clusters. And since it's clusters minus strata, that's why you can run out of the degrees of freedom. It's that 31. In my other example, I only had about 15. And so it was really easy to chew up my 15 degrees of freedom running the multinomial logit, because you've got all the different equations running. And so you've got lots of degrees of freedom being chewed up there. In the output here, I get this not testable. And again, I've run out of degrees of freedom. And that's why I get this. And this is one of the places where weighted data, where survey data tend to be very different from the non-weighted data. All right, but we can still calculate our predicted probabilities and get our graph here. Not that I think that's the most informative graph I've ever seen, but the only point is that all of those post estimation commands do work. There's a little bit of a write-up about what I just said. And this part of the help file here is actually super informative. So if you type help J robust singular and read that, it will really clarify this whole issue here. Okay, count models. We're zooming towards the end. I'm hoping to finish right at 4 o'clock. Count models, again, they work the same way that the non-weighted things do, so there's no surprise here. In Poisson, we assume, well, actually, the way the model is defined, the conditional variance equals the conditional mean. If we want to look at that, we can do this. I use the quietly here just to suppress the output. And here's our conditional mean, and here's our conditional variance. And I'm going to say that 45 and 153 are probably not the same number. Likewise, 53 and 215, probably not the same number. And my solution to this is to simply retype my command and switch out and put in NBReg. So in NBReg, you estimate one more parameter. It is called alpha. It's not related to alpha 0.05. It's a different fella named alpha. And estimating that one gets you out of this problem here. So we go ahead and do that, and there we go. We had a issue with a singleton in a strata, so we got that note. That is fine. Notice what is not here, though. You do not get the test comparing back to Poisson, like you would in an unweighted data situation. It's not a particularly big deal, but don't expect to see it because it's not produced here. And this is your alpha value here. All right, so margins works. We can include interactions. No surprise here. Margins works. Okay, that's great. Margins plot, it all works. It's lovely, fabulous. And that's pretty much the end of what I was going to go over. Now, I do have exercises here, and I have one more comment. Whoever asked me about the multiple imputation, you reminded me of something else that I was going to say regarding subpopulations. Some people have asked me about defining the subpopulation so that it does not include, or that observations are not in the subpop if they have missing values on the variables you want to use in your model. In other words, you're trying to create a subpop that has non-missing on all of the variables you're going to use across all of your equations. And as appealing as that may sound, so that you're holding the subpopulation, the same observations are used in all of the analysis, as appealing as that may sound, it's actually a bad idea, and I discourage that. The subpopulation is supposed to be defined based on stable characteristics. It's not that the characteristics would never change, but they are supposed to be knowable beforehand. So, for example, you would know beforehand that I'm female, that I'm white, that I'm of this age. It's something stable and knowable, not something that you couldn't know beforehand, like that I'm not going to answer item number 15, or that I'm not going to answer item number 23. So typically the subpopulation is defined as something on these knowable, stable characteristics, not on arbitrary missing values. So I hope that part makes sense. It has to do with the math involved there, because you're making certain assumptions that are true when you know something about somebody versus something arbitrary, like did you happen to answer item number 15? So there is that. Let me come back here to my exercises. Oh, we didn't do the graphing exercises. If you want to do the graphing exercises, you can. If you want to do the regression exercises, you can do that. I will stay here until 4 o'clock to help anybody who has questions. I would like to open it up now for anybody to ask any other questions about the content that I have covered today, or other things regarding weighted data.
Christine, I have a follow-up to what you just mentioned about subpopulations. So are you saying that the subpop variable has to have no missing data? Because sometimes, you know, something like race, ethnicity, or rurality or something, there's a handful of people who don't answer it. So you're saying it's not possible to do a subpop if that's the case?
Well, okay, there's two issues there. I forget if Stata will error if you're missing on a subpop. If you've got a missing on a subpop, I usually say that you're probably not in the subpop, and I code it as such. But my point was, you don't want to create the subpop by saying, I'm including only those respondents who have complete data on items 15, 16, 17, 18, 19, and 20. I don't want to do that. If you do a subpop based on race, ethnicity, or a subpop on gender or anything else, that's perfectly fine, because that's a stable, knowable thing that's coded in the data, as opposed to just saying, hey, I only want to take complete cases.
So just to follow up there, so you would, like if you're doing a subpop of female, you would code anyone, including missing people, as 0 for the subpop analysis. Is that right?
Yes.
Okay, gotcha.
What other questions?
Christina, a lot of people want answers to the exercises. Would you be able to post them on the website someday?
Yeah.
Okay.
Yeah, I can. That's fine.
Thanks.
Any other questions?
Hi, Christine. Thank you so much for going through this. I found this really, really useful. I guess the question that I have is regarding multi-level data and then survey analysis. Are there any instances that you think doing a multi-level modeling approach is superior to survey setting your data and then running your analysis? And I ask this because I've heard mixed reports from different people. I've heard people say once you survey set the data, you implicitly account for any inherent correlations that might exist in that data. And then, the multi-level folks are more explicit with the way they model their correlations and variances. I was curious as to what your experience was.
Okay, that actually takes us into 3 different kinds of realms. So let me walk through those carefully. First of all, there is a dichotomy within survey data analysis as to whether you do a model-based adjustment or a design-based adjustment. What I have described throughout this workshop is a design-based correction. And that means that I am using different formulas, and those formulas are different from the formulas used for a simple random sample, and they're based on the sampling plan that I actually use. So I have changed the underlying math, and then I've gone forth and done my analysis. In a model-based approach, what they say is they're going to get rid of all of the survey elements and instead include in, say, the regression model or whatever, the multi-level model, all of the variables that were used to create those design variables. So they're going to use the Strata variable as a predictor or the cluster variable as a predictor if the weight was created, however, whatever was used to create those sampling variables, they're just going to use those in the model. I find that to be impractical, and I don't care how efficient their simulations are. I find it to be crazy impractical. I do not want to put in dummy variables for all of my strata and all of my clusters, or worse, the variables that underlie them. That adds a lot of stuff into my model that I don't actually care about. And I don't want that kind of, I don't want to do that. That's too much into my model. Secondly, that assumes that those variables are in the data set and have not been modified. So for example, if you use the 2000 census data, you will read in the documentation that it is a stratified SRS, but the Strata variable is not released with the public use data. Now, they do describe the variables used to create the Strata, and so I went through and tried to recreate that Strata variable, and I failed. And so I wrote to the Census Bureau and said, you know, I'm trying to recreate this, and I come short something like 50 strata compared to what is listed in the documentation. What have I done wrong? And they said, you didn't do anything wrong. We didn't release all of the different levels of that variable to avoid, exposing too much about the identities of the respondents. So the model-based approach, while it may have appeal, doesn't seem to be terribly practical to me. And that relates to your question, because if you're going to do the multi-level model thing, you have to go the model-based approach. And so you're working on a bunch of assumptions that typically are untenable. Okay, you don't want to put in that many predictors in the model, and you don't even know that you actually have them available to you to be put in. So, you know, the theory might be sound and their simulations may look great, but in reality, I don't know how useful it really is. Now, if you want to talk about a weighted multi-level, which does exist and you can do that, the trick with that is that the cluster variable has to be a level in there, and you have to have weights at each level of the multi-level model. And both of those tend to cause problems for people, and they are some of the problems that come to me during consulting. When I do consulting at UCLA, that's one of the very common problems with this. And it's really quite a struggle. And so the multi-level thing is very difficult. That's another topic that I cover in the advanced survey data analysis workshop. But it comes with its own set of headaches. But the actual answer to your question is the model-based stuff tends not to work very well, especially with the American surveys. Some of the European ones, it does work well. because they only have 3 strata and no clustering. And if that is true, then that's easy to work with, but I've never seen a US based survey released like that.
Yeah, thank you so much. What I'm hearing is, if I can, I should try and survey set my data rather than do the multi-level approach.
Yes, you're right. But one of the things I left out of this workshop is that there's 2 ways to write the survey set. The way that I show in this workshop is how to write it for a single level model. There is a completely separate syntax for how to write it for the multi-level model, and you would have to use that syntax to use the SVY prefix.
Gotcha. Thank you so much.
Yes. What other questions?
Hi. I usually work with DHS data. And I find that usually when I run logistic regression, then all of my factors are significant. And you mentioned something about having more power. So I just want to ask you, how do I really get to know if a factor is really significant if I have got data that is very huge?
Right. So there's a distinction made between being statistically significant and being important in the real world. They have all different phrases for important in the real world, clinically meaningful, whatever you want to call it. And that's where this distinction comes in. So what happened over time was that people started confusing statistical significance for what is important in the real world. And the thing to do is go back and make that distinction. And sometimes I will admit that is easier said than done. So for example, you might say you got an odds ratio of, I don't know, 1.5. You have to tell me, in the real world, does an odds ratio of 1.5, is that really important? Is that meaningful? And sometimes the answer is real obvious, and sometimes it's really not at all obvious. But that's where you have to stop and think about the results much more carefully than just looking down that column of p-values and saying, okay, which one's greater than, which one's less than 0.05. Now you have to really look at something and say, well, is this odds ratio important? And then you look at the standard error and you say, well, at least it's very precisely estimated. That helps me a little bit. Or if you say, this is a really large odds ratio, maybe it's an odds ratio of 5, but the standard error is huge. And I'm like, boy, I don't know if it really is 5. It could be, as small as this or as large as that. So maybe I don't take that one as seriously, and I look at some other things. And so there's a lot to really think about other than just p-values. Now, I have seen some people say, well, instead of using 0.05, use 0.01 or 0.001 or some other cutoff for statistical significance. But I think that's just kind of kicking the can down the road. And it may really be time to stop looking at p-values to tell you what is important and looking at those coefficients instead. But that assumes that you know what is important for that variable in the real world, and you may or may not know that. Does that answer your question?
Oh yes, it does. Yeah, because yes, because there is clinical significance and there's statistical significance, and
yes,
so you always have to check that. Thank you very much.
Yes. Any other questions?
Do you have any directions for looking at longitudinal analysis with SVY? Like anything we could look up ourselves, or I know it's beyond the scope of this course.
When you say longitudinal, I assume that you mean something like time nested in participant.
Yes.
Okay, that pretty much moves you over into the weighted multi-level model situation. And some of the data sets, especially like the time use data sets that I have seen, and some of the other ones, they have been released with time level and person level sampling weights. And so you have to rewrite, you have to use that alternative syntax for SVY and use that. And then you have access to, I believe, most of the multi-level commands there too. That's probably where I would start with that.
Thank you.
Yes. One of the things that I forgot to put in there is looking at the help file for SVY estimation. And the reason this is helpful is because it gives you the full list of commands that respect SVY. And it is an impressive list. Stata has more survey commands than any other software package. And it is really very cool. What I like is that the extended regress is in here. I think that is super cool. I have never actually found a data set where I could use the TOBIT or the trunk reg, but I would love to see such a data set. You can use SEM and generalize SEM, which is super cool. There is survival stuff. Lots of stuff with respects to binary responses. Again, I haven't had the privilege of using a lot of these commands, but they are here for the discrete responses. Wow, nobody comes close to matching this. I haven't actually seen a fractional response regression with survey data, but that is super cool. Here are a bunch of other commands that SVY respects. IV stuff, instrumental variables. I'm not even sure how I would have a Heckman model with survey data, but I guess it's possible. The multi-level commands are listed right here. I have not seen any finite mixture models with survey data, but boy, there's a lot of those commands. I've also not seen any of the IRT stuff with survey data, but now obviously that is there. One point to make though, just because some of these commands exist doesn't mean your data set's going to allow you to do that. So for example, if you use the SEM command to actually do a structural equation model, let's just keep it simple. Let's say you have a simple path model with just one mediator. Most survey data sets aren't set up to allow you to talk about causality. They're only set up to allow you to talk about relationships between variables. So just because you can mechanically run the analysis with the data set and respect the survey elements there doesn't mean that it logically makes sense. So in NHANES, I can't figure out how I would ever run a structural equation model, because at a bare minimum, I have to say that my cause happens before my effect. And in NHANES, I could never tell you what happened first and what happened second, right? And so even though these commands exist, they're not, doesn't mean you can just use them with any of the data sets. Now, I have actually seen data sets. I was actually fortunate to work with one where it really was weighted survey data and it really was an experiment that had been done countrywide. And so we were able to get that causal element in there. And then these commands worked great. But that was a really special data set where she had gotten permission to do this experiment across the country. And so we did have all that sampling, but we also were able to put in that causal element, and you don't see that causal element much in the big public use survey sets. Speaking of all those other survey sets, this is one of the fact pages on our website, and it talks about how to write the survey set command for a bunch of the commonly used data sets. So like the American Community Survey, this is what the survey set command would actually look like. And I have the setups for AdHealth, CHIS, Current Population Survey, the General Social Survey, LA Fans, NHANES, both continuous and NHANES 3, and some of the other data sets. Not that it's important for this group, but there's also the setup for SAS and Sudan. And as time permits, I'll probably put up the code for Thomas Lumley's R package and put that set up in here as well. But this page can be helpful for folks. For example, we talked about replicate weights. So you're given a sampling weight and then a series of replicate weights here. And these are these 80 variables here, up here for the American Community Survey. These are the SDR weights. There's the series of 80 weights here, and these are the replicate weights, and they're specified differently because these are SDR and the others were jackknife, and then others are released as BRR, or balanced repeated replication. And so if that is helpful to folks who are using other public use survey data sets, you can find sample setups here. So you've got an idea of what it's going to look like and what kind of variable names to go looking for in your data set. Any other questions that I can answer?
Christine, I have a question. How do we estimate the power in a regression analysis in the context of survey? Is Levi?
Power. Aha. That is not an easy question to answer. Are you trying to do a priori, where you're trying to say how many how many subjects am I going to need, or are you looking retrospectively and doing a post hoc one to say I had enough power?
I really don't know, because actually I saw a reviewer for that question in a different context, and then so I just asked that. I just assume that possibly the potential reviewer or question and ask me about the power.
Right. The answer is different if you're doing post hoc versus prospective. If you're doing post hoc, I usually refuse to do it because there's no point in doing it. And if I had a statistically significant effect, then of course I had enough power to detect the effect, because I did detect the effect.
Mm-hmm.
If I'm doing it prospectively, then typically, well, one way to do it is in G-Power, and I've had to do this when I was using a very specific subpopulation. So it was children of a particular age who were categorized as obese based on their BMI and had, I don't know, some other issue, whatever it was. And so it became a very small subpopulation. And so in G-Power, you can do a kind of a, you give it, this is my potential n and my potential effect size, and then it will bring you back the power. And so
Thank you.
I did it that way to address that. But really the only time you ever get asked about power is when you're talking about a subpop, and usually a fairly small subpop.
Okay, got it. Thank you.
Yes. What other questions as we wrap up? Because it's just after 4 o'clock here in California. And so first of all, I'd like to thank everybody who came. Thank you to the 31 of you who have stayed here to the bitter end. I appreciate it. If you have more questions, I am happy to stay for a few more minutes and answer those. If you don't have any questions and you need to be elsewhere, which I totally understand and respect, thank you for coming, and we hope to see you at another workshop soon.